Greetings. In today's video, we will be looking at the physical properties of damped harmonic oscillators. First, we will introduce the general form of the damped harmonic oscillator, and then we will solve for a general solution. And for such general solution, there are three corresponding cases for the damped harmonic oscillator. Firstly, the overdamped case, secondly, the critically damped case, and finally, the most interesting one, the underdamped case. After this, we will end the video with some real-life examples of the damped harmonic oscillator. Now we will give a brief overview of the lecture and some overview of the previous lecture. In the previous lecture, we looked at the simple harmonic oscillator, which is typically idealized as they do not take into account frictional or drag forces. In this lecture, however, we will look at how harmonic oscillators behave under the influence of linear drag forces. It is important to note that when dealing with drag forces, they are typically proportional to the velocity. However, it is possible for the drag force to be proportional to the velocity to the power of n. But typically, such equations do not have trivial solutions and would require numerical or perturbative methods to solve. Hence, in this video, our main focus will be on the frictional forces that are proportional to the velocity. Now we will look at the general form of the damped harmonic oscillator. Consider a spring mass system with a drag force proportional to the velocity of the mass by some coefficient b. Then the equation of motion can be written as follows. To simplify the algebra, let beta equal to let beta be equal to b over 2m, and let omega naught squared be equal to k over m. Then the equation of motion simplifies to the following. This is the general form of the damped harmonic oscillator, and it is simply a linear second-order homogeneous differential equation. To solve this, one can apply the following ansatz, and substituting this back into the second-order differential equation, we obtain the following equation, which is an auxiliary equation. And to solve for lambda, one can use the quadratic equation. Substituting the value for lambda back into the ansatz yields the following general solution for the damped harmonic oscillator. From here, one may see that there are three cases for this following solution. Firstly, the overdamped case, where beta squared is greater than omega naught squared, the critically damped case, where beta squared is equal to omega naught squared, and the underdamped case, where beta squared is less than omega naught squared. And these three cases can be depicted on this diagram, which is obtained by the very good book, Classical Dynamics of Particles and Systems by Marion and Thornton. One can see that both the critically damped case and the overdamped case are strictly decreasing. However, the only one that is oscillating is the underdamped case, which we will explore later. But first, let us look at the overdamped case. The overdamped case is when beta squared is greater than omega naught squared. This is because this results in overdamping because the exponents in the radical of the general solution become real quantities, and from this we obtain the following equation. However, it is important to note that omega sub 2 does not represent an angular frequency, as the motion is not periodic. The displacement will asymptotically approach the equilibrium position, and such behaviors can lead to three different cases for the position plotted against time. Given that the initial condition at time 0, the displacement is greater than 0. Firstly, let us look at the first case, where the velocity at time 0 is greater than 0. When the initial velocity is greater than 0, x of t reaches a maximum and approaches 0 exponentially. On the other hand, for the initial velocity less than 0, and for small velocities, the displacement approaches 0 monotomically. And finally, when we look at the velocity, when the initial velocity is less than 0, but for a large magnitude of velocities, we can see that x of t crosses the t-axis and becomes negative, but reaches a minimum and approaches to 0. Now we will look at the critically damped case. For the critically damped case, beta squared is equivalent to omega naught squared. Hence, the roots of the equation of the auxiliary equation are simply repeated roots, and hence the displacement x of t must be written in the following form, where a and b are different amplitudes. What is most interesting is that given a set of initial conditions, the critically damped oscillator will approach equilibrium at a more rapid rate than the overdamped and the underdamped case. This is extremely important in the development of galvanometers, where the system must return to equilibrium as rapidly as possible. And finally, we'll be looking at the most interesting case, which is the underdamped case. In the underdamped case, beta squared is less than omega naught squared. Thus, if we let omega 1 be equal to square root of omega naught squared minus beta squared, we find that the displacement x takes the following form. Note that this solution is identical to that of the one-dimensional simple harmonic oscillator, and hence the solution can be written as follows. This yields a solution that has an oscillatory motion, and omega 1 can be thought of as the oscillation frequency. However, it is important to note that in a damped harmonic oscillator, it is impossible to define a frequency because the motion is not periodic. Moreover, note that there is the decreasing exponential term in the equation. The result of this is that the amplitude is bounded by plus or minus a to the e minus beta t, creating an enveloping effect, as seen by these two dotted lines, and the actual equation for the underdamped case is represented by the solid line and envelope between the dotted lines. Furthermore, if we take the time derivative of the position, we obtain the following. To do this, what we're doing here is to determine the positions of the maxima, and after some algebra, we find that tan omega 1 plus some phase angle is equal to minus beta over omega 1. Given that tan theta is periodic with pi, the maximas occur with time intervals delta t equal to 2 pi over omega 1, and from this, one also finds that the ratio of the maxima is a constant. However, another interesting property of the underdamped harmonic oscillator is that the total energy E is not constant. By chain rule, one finds that the power, which is the derivative of energy with respect to time, is as follows. And using chain rule, we can write it as the following. By substituting the expression for the velocity of the damped harmonic oscillator, we obtain the following equation. And given that the velocity at the maximum is maximum at the equilibrium position, this means that the system loses the most energy when it's moving across the equilibrium, as the sign in front is negative. Now we will look at a notable example of the damped harmonic oscillator. Circuits that consist of inductors, resistors, and capacitors can be modeled as the damped harmonic oscillator. If we let the inductance be L, the resistance be R, the capacitance be C, and the charge be Q, one finds that they can be all written as the potential difference, as follows. So V equals Q upon C, the charge upon the capacitance, which is also equivalent to the voltage times the resistance times the current, and the inductance times the time derivative of the current. Given that the current is defined to be the charge per unit time, the potential difference should be the potential difference should be constant throughout. This means that the sum of the potential difference in each component should be 0, and therefore we yield the following equation. Rearranging and rewriting the terms, beta equals R over 2L, and omega naught squared be equal to Q over LC, one obtains the equation for the damped harmonic oscillator, and hence the general solution is as follows. And for different values of beta squared minus omega naught squared, we obtain the solutions for the overdamped, underdamped, and critically damped case. This marks the end of the video, and in the next video we will be looking at driven harmonic oscillators. Basically, harmonic oscillators where the equations are not homogeneous. Basically, this term on the end is not 0. And thank you for watching, and hopefully you learned something new about damped harmonic oscillators. Please subscribe and like to this channel to get more to get more videos on physics.